Today, we want to take a look at the next big thing, which is sequences, series, and power series. What we're looking at here is a different kind of infinity than the infinity we had before. We're still doing the same kinds of things with it, looking at a bunch of things, adding those things up, plugging into functions so then we add up things. We have an infinite number of things, but this is a different style of infinity than we had with integration. In integration, we were making a sum over a continuum. There was nowhere to put the plus sign. In sequences, series, and power series, we got this discrete style infinity. We have a place for the plus signs, but we need an infinite number of plus signs. So there's a place to put the plus signs because we have discrete terms, but we need an infinite number of plus signs. So that's how it's the same. That's how this is different. That's why this fits in Calc 2. Let's talk about the three objects that we're going to be looking at. The most important one is the last power series, but we need to be previous to get there. We've got sequences, which are just lists. Notice that I have a bunch of terms and they are separated by commas. That's just a sequence. It's a list. A series is a sum. So I just have a bunch of terms, but instead of separated by commas, I am adding the terms together. A1 plus A2 plus A3 and so on. That's a series. For a power series, we're dealing with a function. There's a variable in it. And the form of the function should look like an infinite degree polynomial. I recognize that it does not make sense to say infinite degree polynomial. Polynomial should have a degree, which is some integer. And infinity is definitely not that. But look at the form of the power series. It looks like a polynomial, but it has a dot, dot, dot at the end. So it's a power series, not a polynomial. The important thing to recognize is that the power part is always the same. It always has to be the same power of x minus constants. So in this case, a is a constant. I will refer to that as the center of the series. And then the c's are all constants. So c is constant for all I. These are the coefficients. And a is also constant. Note that we've got only one a. It's not ai for all I, it's just one a that's constant. So all those terms have to have the same form. Some integer power of x minus a. I will usually refer to a as the center of the series. I'm not sure where I picked this up, but that's the language that I use. Actually, I refer to this because a is going to be the center of the interval of convergence. So I'm going to refer to it as the center. So I guess I do know where I picked this up. Actually, check that. I know why I picked this up. I don't know where I got this from. So those are the things. A sequence is a list, a series is a sum, a power series is a function. Let's talk about an overview of how things work. What we want to know is when a sequence, a series, or power series converges. That's going to be our big idea. The thing that we want to know about any of these objects is about convergence. Convergence means different things depending on what we're talking about. Convergence of a sequence is a different idea than convergence of a series. So let's briefly discuss convergence of a series. Convergence. We say that a sequence converges. Actually, there's a better way to write this definition, but I say a sequence converges if the terms have a limit. A sequence converges if the terms have a limit. This has been shortened. I leave off the as n goes to infinity part because that's the limit we're mainly concerned with. A sequence converges if the terms have a limit. That's what I'm normally going to say. What I mean is that the terms have a limit at infinity. So if the limit as n goes to infinity of the general term exists, then the sequence converges. Otherwise, we'll say that the sequence diverges. You may notice that this is a very unusual way to pronounce the word diverges. We'll say diverges. We'll like emphasize that first part. I think it's because we have con and di and they're both attached to converges. So I don't know why I can say converges normally, but I always say diverges. Maybe it's an American thing. I don't know. So a sequence will do one of two things. It will converge or diverge. So here is a nice sequence: 1, then 1/2, then 1/3, then 1/4. We want to turn this into a function of the index n. So the general term, we would say Sn is 1 over n. So if I want to describe this series, I can say the general term is 1 over n for n starting at 1, for n greater than or equal to 1. This is how you write the general term. This is where you write the general term. Since the limit as n goes to infinity exists, this is equal to 0, the series Sn converges. The series 1 over the sequence 1 over n converges. So when we're looking at this, we have the numerator of 3579, so we have odd numerator over 712, 1722. The denominator is increasing by 5. So we want the general term. The general term of this sequence, we start off at 3 and add 2 every term. And in the denominator, we start off at 7 and add 5 every term. And then we start off with 3 7. So we start off by adding 2 and 5 0 times. So n greater than or equal to 0. There's the general term for the sequence. When we're listing the values of n that we're going to be using, that's about the beginning of the series. When we're asking about convergence, we're more concerned with what's going on at the end of the series, even though there's no end, it goes on forever. We take the limits as n goes to infinity of 3 plus 2n over 7 plus 5n. As n goes to infinity, 3 and 7 become irrelevant. We have 2 billion over 5 billion. So we have a ratio of 2/5. The limit exists, so the sequence converges. Since we're talking about the convergence of a sequence, we could say that the sequence converges to 2/5. The limit of the terms is 2/5, so the sequence converges to 2/5. Here's a sequence that just alternates between ones and negative ones. If you want to represent alternating, you can use a power of -1. So we could write this as Sn is -1 to the n. We have to decide where we're starting, and we'll start off where n equals n greater than or equal to 0, since we start off positive. Since the sequence starts positive, we'll write this as -1 to the n for n greater than or equal to 0. This is not the only way we can get alternating starting positive. It could be that we don't want to start for n greater than or equal to 0. We're like, well, I don't like starting counting at 0 for reasons. There might be some other stuff going on. Here, all we have is the alternating 1. So if, for example, we wanted a variation on this, so we bring this to the customer, and the customer's like, oh, man, I don't like starting counting at 0. Start the counting at 1. That's how I count. So fine. This is a matter of taste, so we got to go with the customer. I can still write -1 to the n, but that would start off negative. So I'll just add 1 or subtract 1. So now my first term is going to be -1 to the 1 plus 1, -1 squared, which is +1. Or we can write -1 to the n minus 1. Those will both start off positive. But now I'll start off with -1 to the 1 minus 1. That'll get 0. We just need to be off by 1 to make sure that we start positive. So good news. You have control with how your counting works at the beginning, at the start. Bad news, you have control over how the counting starts. But this is how we make things alternate, a -1 to the n. From a convergence standpoint, this sequence diverges because the terms do not have a limit. So the limit, as n goes to infinity, of -1 to the n, or -1 to the n plus 1, or -1 to the n minus 1, does not exist. So therefore, the sequence diverges. So the values of the terms of the sequence are not approaching anything. So the terms don't have a limit. So the sequence diverges. It's important to remember that a limit that heads off towards infinity does not exist. You are not approaching any value. If the limit of the terms is infinity, the limit does not exist. So for example, this sequence 1, 2, 3, 4, the terms are headed off towards infinity. So the sequence diverges. You don't want to say that the limit of terms equals infinity, because just saying equals infinity doesn't make any sense. The limit of the terms go to infinity. The limit of the terms does not exist. The sequence diverges. So what we're saying here is that the terms go to infinity. The limit does not exist. the sequence diverges. The terms go to infinity, the limit does not exist, the sequence diverges. If you start mixing these up, people will probably get what you're saying, but you're saying it wrong. You don't want to say that the sequence doesn't exist. The sequence is 1, 2, 3, 4. The sequence exists. It's right there. It's that list of numbers. If you say the sequence does not exist, you're not making any sense. Even though you're kind of making sense, your fellow students will know what the F you mean. But I, as the instructor, even though I know what you mean, I have to pretend like I don't know what you're talking about. And I do it in an incredibly dickish way. I'm like, oh, what do you mean the sequence doesn't exist? It's right there. And that's just me reminding you that does not exist is a phrase that goes with limits, not with sequences. For sequence, you only get to say converges or diverges. You also don't want to say the terms don't exist. They're for the same reason. They're the terms right there. The terms go to infinity. The limit doesn't exist. You also don't want to say that the limit diverges, because that's not what we're trying to say. We're trying to say that the sequence diverges because the limit does not exist. Does that make sense? This is why if you use the word it, I just automatically mark shit wrong. If you're like, oh, it diverges, I'll be like, oh, what diverges? And then you have to point to the instructions where it says determine if the sequence converges or diverges. And you'd be like, well, obviously I'm talking about the sequence because that's what the question was about. And I'll be like, oh, fair play. But then if you're like, oh, it diverges because it does not exist, now I don't know what you're talking about. The sequence diverges because the limit does not exist. And if all you say is, it doesn't exist, then I will just mark it wrong. So, best policy for students, don't use the word it. If you're about to use the word it, make sure that you're very careful what you are referring to when you write the word it. I'm not teaching linear algebra over the summer, but I just straight up outlaw the word it on the first day of class. I am the only person in the room that gets to use the word it because I need to use it as a quiz question. If I say it is inconsistent, what am I talking about? So. Careful with your phraseology. Also, I wrote terms go to, it's like, I kind of should have separated. I should have just switched pages. But I didn't, so there we go. Any questions? A sequence is a list. A sequence converges if the terms have a limit. That's the simplest of our three objects: sequence, series, power series. Because that's what we need to know. We say that a series converges if the sum is finite. crazy. Just like with sequences, we will want to know what the general term of our series looks like. But because we're talking about a series and not a sequence, we can't just write the general term. We have to say we're finding the sum of all these general terms. So we will use summation, sigma notation to represent our sums. So it's very clear that we're talking about a series that have a sigma an, the series an. I will usually read this as the series an rather than sigma an or sum an. Sometimes once we're really into it, I will just write sigma an and just say an, and it'll have to be clear from context which one I'm talking about. The important part of the summation is that there are an infinite number of terms. If there's a finite number of terms, then convergence isn't even a concept that we need to bring up. There's a finite sum, a finite number of terms on a finite sum. That's not, the convergence is not even a question. The other thing that we need to notice is that our shorthand is not going to have where we start. Because the important thing for converges is that there are an infinite number of terms. What happens at the beginning is not important. The critical stuff is what happens as n goes to infinity. So our shortened notation leaves off where the series starts, whether we start the counting at 1 or 0 or 10. If the sum of an infinite number of terms is finite, then cutting off 10 terms, the sum will still be finite. If the sum of an infinite number of terms is infinite and we cut off 10 terms, the sum will still be infinite. The important part of the notation is the implied infinity at the top. So our shortened notation, we're just going to write a sigma, and I'm going to write it in my lazy sigma way, sans serif and all rounded instead of all angular. This is because I learned calculus in the 90s and it just can't follow Cardinal, I think. So in the 90s, we were getting away from the angular wedge shapes of the 80s, and then everything was becoming more rounded. This is why all cars from the 90s look like blobs. This is a much more complicated question. Once we have an infinite number of terms and we're trying to add them up, it's very difficult to determine if we're going to end up with a finite sum or an infinite sum. So this is a super messy question. We're going to have to learn which series converge on sight. The goal is to look at a series and know that it converges or diverges immediately just by looking at it. It's framed as a test for convergence. And we're going to learn how to write properly the test for convergence. But the goal is to just look at a series and say diverges or converges. More specifically, it's three choices. Diverges, converges absolutely, converges conditionally. The goal is I give you a sheet, the form is I give you a sheet of paper and I start handing the sheet of paper out at one side of the room. As soon as I get to the other side of the room, I walk back to the front and I start collecting it. You get the amount of time it takes me to hand out the quiz to do the quiz. Now, we're not doing quizzes on paper and I don't put time limits on. So you're just going to have to be your own judge. But if I give you 12 series, you have to determine converges, conditionally, converges absolutely, diverges in about 30 seconds, depending on your internet speed. The only thing that should be slowing you up when you make this decision is your internet speed when you hit submit. You have to know by looking at it. Here's why we have to know by looking at it. In the case of a power series, when we plug a number into a power series, we get a series. If we take a real number as an input to a power series, the output is a series. The output of a power series is a series. This is why we have to look at a series and decide if it converges immediately. The output of a power series is a series. So in the case of a power series, we have to know what can we plug into the power series so that we get a convergent series. So when we're dealing with a power series, we have a slightly different question. We're asking for what values of x, for what inputs does the power series converge? And that means the output is a convergent series. Remember, we're thinking of a power series as a function. There's an x running around in it. We're imagining that this is a function. That means we can evaluate this power series. We can use a bunch of inputs. When we put an input into the power series, it goes in for the x, and we end up with a series. So if I wanted to calculate P of, let's say 1, I get 1 plus 1 squared over 2 plus 1 cubed over 3, and so on. We plug in a 1. The result is a series. The input was 1, and the output is the series 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 so weiter. The input is a 1. And the output is this series. We need to be able to look at this series and immediately identify this as a divergent series. We need to immediately look at the series and say, when we plug in 1, we get the series 1 over n, and that series diverges because that's our future math knowledge. And so we would say that the power series diverges when x equals 1. Because the series diverges, that tells us that this power series diverges when x equals 1. We might also say the power series diverges at 1. We haven't learned the parts where you look at the series 1 over n and immediately conclude that immediately decide that this series diverges. But it does. Right now, just take my word for it. If I plug in a different value for the x, I will get a different series. So if I change my input to something else, like 1/2, here's what our series looks like. X plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and so on. There's our input of 1/2, and our output is a series. If we clean this up a little bit, we'll start off with a 1/2. The next term will be a 1/2 squared over 2. The next term will have a 3 and a 2 cubed. The next term will have a 4 and a 2 to the 4th in the denominator. So for this here at this power series, we have an input of x equals 1/2, and our output is the series 1 over n times 2 to the n. When we look at the power series 1 over n times 2 to the n, we will decide this series converges. Absolutely. And so that will allow us to conclude that the power series converges when x equals 1/2. So because the series converges, that allows us to conclude that the power series converges when x equals 1/2. We still don't know this part, how we know that this series converges absolutely just by looking at it. That's our goal. Before, when our functions are just outputs, and we were trying to say, okay, we want functions of real numbers, we just have to look at the output and see if the output is a real number. Is it the square root of a negative? That's complex. That's not an output, so whatever input produced that is out. Or if the denominator is 0, then that's out. Now we have to be able to look at the output and decide if it converges or diverges immediately, so that we can see if the power series makes sense at that point. So that's it. That's intro to sequences series power series. A sequence in a list converges if the terms have a limit. A series is a sum, converges if the sum is finite. A power series is a function whose outputs is a series. That's why we want to be able to identify if a series converges or diverges on sight. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.